Let's continue our discussion of the number e and scroll down to the bottom of this page. And before we actually use e in a compounded interest problem, I just want to back up a little bit and talk about the fact that e is the natural exponential function. And so far we've graphed exponential functions with integer bases and also with fractional bases. And here, e is considered an irrational number, and y equals e to the x is considered the natural exponential function. And if you want to graph that, e is approximately equal to 2.7. So when you're graphing in e to the x, well, we used to have -1, 0, and 1. -1 would be 1 over e, or approximately 1 over 2.7, which is roughly a third. And again, we're graphing these by hand, so you're going to eyeball that at around a third. 0, e to the 0 is 1, e to the 1 is just e, or approximately 2.7. So you can see that at 0, 1, here's the graph of e to the x, it goes through 1, 2.7, and -1, approximately a third. And so y equals e to the x is an exponential function that really falls between 2 to the x and 3 to the x, although closer to 3 to the x. So it is possible to graph the natural exponential function just as you graphed other exponential functions. You're just approximating. All right, so let's move on and use the what is called the continually compounding interest formula. And so the model is a equals PE to the RT, and we're not going to prove where this one comes from. It's a little more advanced than this class, but let's learn how to use it. So it says suppose that 3,000 is invested in an account with a 4.25% interest rate compounded continuously. What would the investment be worth after 8 years? Round your answer to the nearest dollar. So we know we've got a principal of 3,000 and we're looking for the amount. So A will equal the principal, which is 3,000, times e to the 0.0425 times t, and what we're going to do is we'll evaluate this in our calculator. So we'll do 3,000. Now there's two e buttons. There is an e that is above the division symbol, and that's just a plain old e. And then there is an e to the x, which is above this natural log button, ln, which we'll discover later. So I'm going to use second and then ln, and that will automatically raise the exponent for me. And then up there I'm going to open parentheses. Even though my calculator, I don't need them, on most calculators you do, so we're going to type 0.0425 times 8 and close those parentheses and then hit enter. So our value would be worth $4,215 after 8 years. Now let me show you how to use the other key. It's up to you. It's your choice. We're going to evaluate the same expression, 3,000. If we multiply that by e using the second division key, you see how now that just gives us the number e and it doesn't raise it to the power. So in this case we then have to hit the caret key, and then we would type in open parentheses 0.0425 times 8 and close them, hit enter, and you can see you get the same exact thing. So you have two options on the e key. If you use the one that's above the division symbol, you have to use the caret key to raise the exponent. If you use the one that is above the ln button, then it automatically raises it. So what I'd like you to do is pause the video and try one of these problems on your own. Here we have $18,500 to be placed in an account that advertises 7.12% annual interest rate compounded continually. How much is the account worth after 4 years? So this is a compounded interest problem. A equals PE to the RT. The principal is 18,500. E to the R, which is 0.0712 times 4. Okay. Type that in our calculator. 18,500. I'm going to use the E to the X button. Open parentheses 0.0712 times 4. Close them. Hit enter. And we get, if we're rounding to the nearest dollar, we get $24,596. So the compounded interest formula is actually, I think, easier to use than the compounding by a specific amount. And also, if you want to find a principal given an amount, the similar formula is, it would be P equals AE to the negative RT, and that works similarly to the other formula.